Hey guys, let's try to solve this problem in HDLBits. This problem is called population count, and our task is to count how many of the bits in the input vector are equal to 1. The input vector has 3 bits, so a input can look like this. We have 0, 0, 1. This would be a valid input, and you can see that only one of the inputs is equal to 1, so our output would be 1. Another input could look like this, 1, 0, 1, and you can see two of the inputs are equal to 1, so in this case we would output 2. You can probably think of a solution that would include counter and loop that would look at each of the bits and increment the counter every time you see 1. This would be a valid solution to this problem, but in this case we are not allowed to use loops and sequential coding, so we have to figure out another way that would include just combinational circuit. So we will look at solution that will be valid for this problem. But before we try to solve it, let's look at this problem, because understanding this problem will help us in understanding how we can solve the population count problem. In this problem, we are given a truth table, and our task is to create a combinational circuit that will implement this truth table. So first we have to look at the rows where the output is equal to 1. So that's row 2, 3, 5, and 7. And we will OR all of these rows. First, let's look at row 2. So we have these inputs. So row 2 is equal to not x3 and x2 and not x1. So we can write it as not x3 and x2 and not x1. So this is how our row 2 will look like, and the final output will look like this. Out is equal to row 2 or row 3 or row 5 or row 7. So this is how we can solve this problem. We can also look at easier problem. In this case we have two inputs, x1 and x2, and our task is to find XOR between these two inputs. So that means only if x1 or x2 are equal to 1, but not both. So if both or none of them are equal to 1, then we output 0. And we look at row 2 and row 3. That's our rows when output is equal to 1. And we will OR these two rows. And the rows will be equal to not x1 and x2, or x1 and not x2. So that's our values here. Let's look at one more example, and here we will try to understand how we can simplify the final circuit. Here we have input x1 and x2, and our output is equal to only x1. So that means row 3 and 4 are equal to 1. And this is the final circuit, and you can see it's quite complex. But we can reduce the number of elements in the output by looking at the rows that have the same values for all of the variables except for 1. So row 3 and 4 have the same value for x1, but different value for x2. So here, if x1 is equal to 1, then the output will be equal to 1 no matter what value has the x2. So we can get rid of x2 and the final output will be just equal to x1. So this is a reduction that we will use in the truth table problem. Now that we understand how we can simplify the final circuit, let's look again at truth table problem. And I already have a working solution here that includes all of the 4 rows, but let's try to simplify this function. If we look at the rows where the output is equal to 1, we can see that here in row 2 and 3, x3 and x2 have the same value, but x1 changes. Also in row 5 and 7, the x3 and x1 have the same value, but x2 changes. So we can further simplify this. So let's do that now. And here you can see this is the same for both of the row 2 and 3, only x1 changes. So we can get rid of x1 And the final output can just look like this. And in the other case, x3 and x1 have the same value, only x2 changes. So we can again get rid of x2 and we can get rid of the other function. And the final output can be reduced to this. So let's try to submit this. And you can see it worked. And finally, let's look at the population count problem and let's see how we can solve this. Here I have a truth table with all of the combinations for the 3-bit input vector, and also in the right column here I have counted how many of the bits in the input vector are equal to 1. For example, in this row you can see that there are 2 bits equal to 1, so the count is equal to 2. Let's look at the output. Our output will have 2 bits and it will represent the binary number of the count. So it can have values 0, 1, 2, and 3. And we can see that out1, this one, out1, that's this bit, is equal to 1 if there are 2 bits equal to 1 or 3 bits equal to 1 in the input vector. So we can write this out1 as 2 or 3, and out0 is equal to 1 when there is 1 bit in the input vector or there are 3 bits in the input vector. So we can write out 0 as 1 or 3. And we will implement it the same way as we have done the previous problems. So first we will implement out 1. We will look at the rows where the count is equal to 2 or 3. That's this row, this row, this row, and this one. And we can use the reduction as we have learned. For example, in these 2 rows, in 3 and 2, they are the same, equal to 1, but in 1 is changes 0 and 1. So we can get rid of in 1, and we can just write in 3 and in 2. The same in this row and this row. Here you can see in 3 and in 1, they are identical, but in 2 changes. So we can get rid of in 2 and we can write in 3 and in 1. And in this row, we can't use reduction. So we will have to write the whole function, and that's in 3 or not in 3 and in 2 and in 1. So not in 3 and in 2 and in 1. And that will be our output 1. And then we can do the same for output 0, but in this case it will be when count is equal to 1 or 3. But in this case we can use reduction. There is no way we can reduce the or we can simplify it, so we will have to write the full function. So the first one will be not in 3, not in 2, and in 1. And then we will OR all of the rows. And finally, let's try to solve it. So first we will do out 1. So assign out 1 equals to, and I will write all of the 3 rows here. The first row is in 3 and in 2, and I'm starting here from 1, but in the assignment we start from 0, so I'll have to reduce the numbers by 1. So in 3 and in 2, or in 3 and in 1, or not in 3 and in 2 and in 1. So in 3 and in 2, and I'll copy this, or in 3 and in 0, and this has to be 2, and this has to be 1 and 2. And the final one will be and in 1, and this will be not. So this is our out 1, and let's do the same for out 0. But here we'll have to write the full. So let's first look at, so out 0, that's rows where count is equal to 1 or count is equal to 3. That means this one, this one, this one, and this one. That's 4 times. So let's create 4 of these. and I will OR them. And the first row is in 3 and in 2 is equal to 0. That means this will be not and this will be not. The next one in 3 and in 1. So this will be not and this will be not. Then look at this. Let's look at this row. Here in 2 and in 1 is equal to 0. So this will be not and this will be not. And the final one, all of them are equal to 1. So we can just keep it like this. And this is the solution for this problem. So let's try to submit it. And you can see we have implemented the design correctly. So if you want to see more problems like this, don't forget to subscribe and I will see you in the next one. Bye.